Okay, so the goal for today's class is to introduce you to the software called Praat, which you hopefully have already downloaded on your computer. There's a manual on how to do that, which you can download from Canvas. You can also view various online videos or web pages on how to do this. This is a really commonly used piece of software in various fields that are related to what we're learning about in this course, particularly linguistics and phonetics, hearing and speech sciences, music science, um, psychology, computer science, so anything where the acoustics of speech and other sounds plays a large role in what we want to understand. And the reason why I want to introduce you to this program is that in the past, I have given presentations where I've used it and I've shown you images from it. And in past years of my teaching, I felt that I was able to demonstrate points, but then at the end of the day, my students weren't able to recreate those same examples and tutorials and activities on their own. So I wanted to introduce you to this so that if nothing else, you walk away with some tangible skill that if you wanted to analyze sound to understand the pitch or the changes in intensity or the acoustic properties of a voice, that you'd have some head start in how to do that. And that could be useful if you're going to be getting involved in research or getting involved in any kind of, um, any kind of quantitative analysis of speech. So hopefully we can all learn a lot about this. I've been using this program for, for 18 years. I didn't calculate it until just this moment, but I guess it's been a long time. So what I'm going to do is share my screen and just walk through the very brief instruction on how to get this, because even though this was available on our walkthrough, I just want to make sure that if you're seeing these motions, if you're seeing these images on your screen, that it's showing up well. So the first thing I'm going to do is go to praat.org, and this is just a little shortcut to get to the actual web page, which is a university site in the Netherlands. And if it looks like this website is straight out of the 90s, it is. They've spent all of their effort, I think, on making sure the program runs well on various platforms instead of updating this website. So there's lots of information on here on how to do various things, speech manipulation and synthesis and analysis and programming using a customizable programming language. The program is very powerful, and it can be usable for people at the whole spectrum of experience. Right? If you're just getting started, like in this class, it's an introductory class, or if you're at the very height of computer science and speech technology, either way, this program could be useful for you. Because I'm on a Windows machine, I'm going to go to where it says Windows up here. So the first, the top left up here is where you get the program. And I'm assuming that most of you are on either a Macintosh or Windows or Linux. But as it turns out, in recent years, there are other versions of this made for other platforms. So I'm going to click on Windows because that's what I'm running on right now. And for the most part, any computer from recent years is going to be a 64-bit computer. So I'm going to click on the first link, which is a zip file that just contains the program. It's already finished downloading here. I'll click on that. And this looks obviously a little bit different for those of you who are on a Mac. And if any of you have had difficulty, maybe if you want to speak up and get help from anyone else in the class right now who has installed it using a Mac, that's good. So when I clicked on that file, what showed up was from my downloads folder, here's the program. And you don't want to run it directly from the zipped folder. Typically what I'll do is I'll actually drag this out to the desktop. Okay. And I've already done it, so I'm not going to do it again right now, but I'll just drag it out to the desktop and it just creates the icon to run the program. So have there been any difficulties in just getting the program up on your computer? Has anyone had any snags with that? Okay, nothing so far. That's good. Okay, so the next major thing that you want to make sure you know how to do is actually getting some audio so you can look at it. And so if you go into Canvas in our Praat folder, I should have called this '08 Praat because last week was for speech production. But in any case, it says Praat. So if you click on that, you'll see first the PowerPoint, which is, you know, just the pictorial introduction on how to do this. But then there's this audio folder that has lots of sounds. And the reason, I mean, there's no particular importance in any of these words except that they could be good for demonstrating particular things about speech acoustics. And for the most part, we'll continue to work with these sounds when we get into speech acoustics. Now, the reason why I uploaded these words is not because I'm so in love with my own voice that I want you all to hear it. It's that if we all are working from the same audio file, we can point to the same exact time, click on the same exact frequency, and get the same answer. So we can have a lot better um, cross comparison between techniques to make sure everyone's on the same page. And then later on, you know, we can record some things live and think about, you know, what that means to analyze things on the fly. So there's a lot of sounds, and I don't expect you to click on each individual one. Now, there is a way of downloading all the sounds at once, and it's a little hard to find. So if right as you see here, if I just click where, you know, where it'll underline the file, it'll just play that sound for me. If I click right here, it'll play it right in my browser. And I don't want to do that every time. And I also don't want to like click over here and then download every single one. But you'll notice that there's this little black line on the side. So if you've ever like dragged to select lots of things, so I clicked here, I'm going to hold down the shift key and then click on the same spot down here. You'll notice how all of these have now been selected. I don't know if there's another better way of selecting multiple things. I haven't found it. But what I'm going to do is actually select all of them. So I selected the top one, and notice it's a very delicate area of the screen I need to, because if I click a little bit too far to the right, it'll just play that sound. But if I click just in that little narrow white region, then I should be able to make my selection. So there's the first one, and I'll click on the second one there, right at the bottom of the list. Now they're all selected, and now I can hit this download button. And when I do that, it's going to compile them all into a folder, and eventually it'll show up in my browser here. There it is. So it's about 3 megabytes worth of sound, which is, you know, not too much. So you can open that up and put it on any, you know, folder in your computer. If you're on a Windows machine, this should look, you know, this should look familiar. I can just Control A to select all of them, Control C to copy, and then I can find some good place to put them. And so I'll, you know, open up my class folder. I can go into the Praat section. Hopefully you have some kind of organization like this. And I'll make a new file folder called audio from Canvas. And I can just drop those files right in there. So I just did that using some keyboard shortcuts. And alternatively, you could just like grab these and just drag them right into that folder too. However you prefer to do that, as long as they're there. I want to give everyone just a moment to make sure they can get some audio from Canvas, because we're going to be all looking at the same things just to make sure, you know, because if you look at a recording of your own voice and then I'm showing a recording of my voice, if things look different, I want to make sure that any differences are things that it's because, oh, because I clicked here and you clicked there, rather than, you know, just our voices being different. It'll help, you know, ease that understanding a little bit. So if anyone wants to, if there are any problems in accessing any of those sounds, please type something into the chat window or activate your mic and let me know. And we can try to work out any of those difficulties. So I would recommend that you download all of them, because it's just as easy as downloading. Well, it takes a little nimbleness in your clicking, but it's just as easy as downloading just one. So I'm going to be hopping back and forth between one sound file and another. So I would recommend to just get all of them, and they're just available in Canvas in the Praat folder. So again, just to show you where they are. Here I am in Canvas, and then in the files section where all the, this is where I put all the lecture slides and things like that. There's a folder for Praat. And then there's a folder that says audio. All right. So I have this audio here. So there are two ways of opening a sound file using Praat. One of them, I can take this and I can very carefully drag that right onto the icon. And now it doesn't let me know that anything happened, but if I click on Praat, like as it turns out, that file is now there. So that's one way. I mean, that's kind of a shortcut. I would recommend instead that you treat this the way you'd treat any program like Word or Excel or whatever, where I can say open, read from file. And just like other programs, if you just hit Control O, it'll also do that. And here I am, and you can just, navigate to whatever folder you saved them in. In this case, I'm in my folder for this class and click on my Praat folder, and I can click on audio from Canvas or wherever you saved it. And I can, click on SOC, and now it's in my list. So there are a couple things I want to say just to make sure people sort of know what's happening as they do these. And before I get to that, just because there are a few things in the chat here I want to address on selecting these sounds. This was probably the trickiest part. So let me go over this. So if you click on any of these sounds, like right here, in fact, I accidentally now just figured out a better way of doing it. So if you click right on the little sort of paper with a dog ear looking icon on it, or the name of the file where you see the thing underline and that underline gets engaged, then it's just going to play it for you right away. But you don't want to do that. You want to save it. So I'm going to click away from that, like on the date, right here. And then I'm going to scroll all the way down, and I'm going to hold the Shift key and click another one right on the date. And now all of them are selected. Okay, so that's how you select multiple ones. As it turns out, you don't need to click that which is good, because that wouldn't have been very good design, right? So I can click right here. I can also just click this one. If I hold the Control key down, I can very selectively identify the sounds that I want. Or if I just hold the Shift key down, it'll select everything between the first and the last selection that I make, okay? And if you hold Shift, it'll interpolate between your two endpoint selections. And then after you have what you want selected, you can just hit this download icon right there. Okay, so I've opened up, I was in Praat, I said open, read from file, and I opened up a file, okay? And now I have this thing in my, what we have up on the screen is called the object list. And you can see that I've already opened up a couple even before I opened that word SOC. But what this says is, we have taken that file from the computer and made a little temporary copy of it for viewing in Praat. And if I make changes to this, if I open up that word SOC and I take almost everything except the K and delete it, I'm not endangering anything on the computer yet because it's just a temporary view of this. And I would have to like go through an extra process to save that, which I haven't done. So what the first thing you want to do when you have your sound in your list is click this View and Edit button. And for the most part, the View and Edit button you can think of as just a view button, because there's not a whole lot of editing you can do from this perspective. But there's a lot of viewing you can do. So these illustrations should look familiar in that we have a sound wave up on the top and we have our zero line, right? Which makes sense. And all of our sound waves are deviating from that zero line. And linked with that is on the bottom, we have the spectrogram. And you'll notice, like, as we have right here, it's sort of a change point in the waveform, so too we have a change point in the spectrogram, right? We have something that sort of looks like one type of energy and one type of frequency dispersion, and now we have a totally different kind of energy and also a totally different representation of what the frequencies are, right? So, and then here in the waveform, we have basically no sound, and in the spectrum or spectrogram, we have no energy. So these things are linked. Whatever you see up top should be perfectly represented by what comes directly beneath it. So there are a number of different landmarks on this screen here. And I'm now in a position where as we're going through this, some of them are just second nature to me. And so as I'm referring to these things, be sure to speak up, whether just get my attention verbally or write something in the chat window and say, wait, what did you look at to get that number? Like when I clicked here and said, oh, this is, 194 milliseconds into the sound. Like, how do I know that? It's because I'm looking in one of two places. Right up at the top, it has this time window or timestamp up here. And also down at the bottom, it lets me know how long this first segment was from 0 up until the time I clicked. So there are a lot of things like that. You can see that there's lots of numbers on the screen, lots of these bars down here showing it duration information. There's a frequency represented here. You see because it has the unit hertz on it. So as I'm going along, a lot of these things I can absorb pretty quick because I've used this for a long time. But be sure to slow me down and say, what part of the screen should I be looking at as I do that? For the most part, I'm going to try to make the cursor follow along where I want you to look, but just as I'm human, my eyes might dart around faster than my hand can. So just taking a quick look in the chat here. If you want to follow along by doing this in Praat as well, if you have a monitor set up where that's possible, that's fine. It might be tricky for you to see all the detail if you wanted to do that. But at the same time, I do think that doing these things on your own is probably the best way of really getting familiar with with all the clicking, the opening sound files, doing things on your own is a really good way of learning. So that being said, I wanted to continue thinking about the specific things that you want to do to just get started and getting familiar. We identify the waveform, we identify the spectrogram. We know that if we look at certain parts of the spectrogram up and down, we're seeing different frequencies. So if I click on this part of the spectrogram right here, we see two really important things. One is, in fact, let me just open this so I can, I'm trying. So what's weird is that the time stamp is getting a little, so it's cut off just enough that you can't see the decimal, but hopefully you'll see that the space between the 0 and 2 is where the decimal should go. And we can see it down here anyway. So, okay, so I'm clicking on this part, and this part is like the lower of the two dark bands. It might look like one dark band, but it's basically two dark bands down here. And so there's a time point that I clicked on, and it'll let me know it's about 0.259 up here. It'll always give you more, more specificity than you need. And it'll say down here, now what this says, it's the same number, but what this represents is not a point in time. This represents that there's 0.259 seconds between the left edge of what I see and then the point where I clicked. So, and then on the left side, we have this number 703.8 hertz, which means within this spectrogram that goes from 0 to 5,000, at this point in that range, this corresponds to 700. So if I see that in the spectrogram, that means that during this speech signal, during this utterance, there was strong energy right around 700 hertz. Right? And I would encourage you to think of these frequency numbers, like you can kind of simplify them in your head, because when I click on this and I see 703.8, I just think 700, because that's just sort of as much specificity as you'd need in the frequency domain. In the time domain, things tend to be a little bit more precise. So here I would at least go out to 3 decimal places. And the reason for that is that 3 decimal places gives us milliseconds, right? Because those are thousandths of a second. So here I would just say 0.259, and I wouldn't even mentally look at the numbers that came after that. I would just say, you know, this is about 260 milliseconds into the signal, right? And so far we haven't really looked or played anything. I'm just looking at timing landmarks, right? So in this case, we know that the word is sock, and I haven't played any of it yet, but we can see that like the first part here is very different. This is probably the first phoneme, right? And here is probably the vowel for many reasons. One, it's the loudest part of the signal, right? We can see that in the waveform. And it has periodicity. We know that we can see a repeating part. And if I can click accurately enough, you can see that these vertical almost stripes in the waveform are relatively equally spaced apart, which means that this is a periodic signal, which is what we'd expect for a vowel. I can click on where that kind of tapers off. Now notice this doesn't have a crystal clear endpoint. It kind of tapers off and then finally reaches a point of silence. And we'll come back to that idea where there might not be a single point in time where things categorically change. It's more of estimating a time. So this estimate is just as good as any other. And we can see that that ah sound, what we think is the ah sound, ends about 450 milliseconds into the signal. Then there's this stretch of silence. And then this little piece, like it almost looks like it was like a little smudge on the waveform. But as it turns out, that's the cut in sock. And so we can see exactly when that happens, 567 milliseconds into the signal. We can see that down here too. And we can also click and drag things, right? As you saw that I did a moment ago. So when I clicked and dragged this, up at the top, we have 4 really useful pieces of information. The first two, like on the edges in red here, we have the starting point and the end point of my selection. And then the middle says this is the duration of the selection that I selected. So that could be really useful. If I want to know how long this duration of silence is, I just click and drag it and it'll tell me 0.120, which is more helpful than like doing this mental subtraction of subtracting 0.565 and minus 0.445. So that's a good way of getting these these simplified duration measurements. So how long is the S? I can select from there to there, about 170 milliseconds, as we can see. How long is the ah? Roughly 255 milliseconds. Then we have this 120 millisecond-ish closure duration. And then the ka is really hard to measure, right? We know when it begins, but it's not really clear where it ends because it kind of very gradually tapers off into what looks like almost silence, but it doesn't look quite as clean as this line. So that's not something that's easy to do. The other landmarks are a lot easier, right? So we have a few things here that are really useful. So another thing that you noticed, that fourth piece of information when I was highlighting this is that we have, in addition to the starting point, the end point, and the duration, we have this other thing in parenthesis, which tells us how many of those chunks of time would fit into 1 second. And you can imagine where this could be useful because it should remind you of how we calculate frequency, right? So if this were the thing that we're repeating, the frequency would be 8.27 hertz, right? 8.27 per second. That's what we're reading here. So in a moment, we'll see why that particular piece of information is going to be really useful. It's not useful here because like this thing isn't repeating many times a second, right? So why would we care about that number? But it's always going to give that to you. And the exception to that is if I click on something that's really short, like this, then obviously within that little gray box, it's not going to have enough room to show me those numbers. It'll show me the starting and ending point, but it's not going to show me all that detailed information because it just doesn't have room. So there are ways of getting it anyway. But if you don't see it, it doesn't mean that there isn't a duration or isn't a periodicity rate. It just means it's too much to fit on that part of the screen. So let me start here. Are there any questions about what we've looked at so far up on the screen here?
How does the spectrogram work from just an audio file?
I want to make sure I understand the question. When you say how does it work,
Oh,
do you mean how it's
like,
computed or?
yeah, yeah. Because the computer doesn't necessarily know like what the air was like around the speaker when it was recorded, but it makes like a picture.
Yeah, that's right. So the spectrogram is computed directly from the waveform. So the waveform that you see is the closest thing to what the actual sound file is on your computer. And in fact, we can turn off the spectrogram just to view the waveform in a little bit more detail. And you can toggle that on and off by, if you click on Spectrum, Show Spectrogram, or you can toggle on and off other things too, like a pitch contour, intensity contour, formants. So what you see on the screen here is the closest match to what the actual numerical contents are of the file. And then what the spectrogram is as you roll along in time, it'll perform an analysis of what frequencies are in this part of the signal, what frequencies are in the next successive part of the signal, what frequencies are in the next part. So those aren't stored in the file, but by analyzing what the contents are in real time, you can compute what the spectrogram will be. So that's how it works on it's a bird's eye level, bird's eye view of how it works. And this next segment that I'm going to get into will give you a little bit more insight on that. I'm going to go into how we can zoom in and look at some extra detail in that spectrogram. But is that sort of addressing the question you have?
Yeah, thank you.
Yeah, and you did mention also, like, the computer doesn't know what the air was like around this, but the microphone does, right? So imagine that you have a microphone, right? This microphone on in the room. It's waiting to collect sound, and if there's no sound, it'll look just like this. It'll just look flat, right? Because there's no pressure pushing it in or out. It's just sort of hanging out. And then as soon as you begin changing the local sound pressure by making sound, the microphone will move up and down. And so what the computer is representing is how much displacement from the original microphone position did you create? So we're sort of dipping in and out of sort of thinking about the electronic systems into looking at the visualization. But these are important things to know, right? Because if you have a lot of background noise, you want to know, was that because of background noise, or was that a person, actually making a speech sound? These are good things to keep in mind. What are some of the other questions we have about what we've seen so far? Are you able to click around on here and see, these pieces of information show up? If you click and drag over the vowel, you can see the duration of that vowel. You can see here the vowel. If you just concatenated this vowel, right, you could fit 3.89 of them into 1 second. Right? These are, I mean, again, that might not seem relevant now, but I assure you, in a few moments, that's going to be very useful information. What do we think? Don't see anything in the chat window. All right, so the next thing I want to do is show you how to zoom in to particular parts of the signal. So right now we have a recording that's just long enough that we can see some very identifiable, visibly identifiable chunks. But what if I'm really interested in the details of what's going on in this vowel? So maybe like the central part of this vowel, I'll click and drag over this segment. It's about 40, let's make it roughly 50 milliseconds long, right? Just like that. Okay, now if I click and drag on that part, you'll see down on the bottom left, there are these little buttons down here. So I can zoom in by pressing in, and it'll zoom in, and I'll continue zooming in until I get down to like the sample by sample level of the sound. Okay, and then I just zoomed out. If I press the SEL button, it'll zoom to the selection that I've made. So because I've made this selection, I'll press SEL and it zooms directly to where I want, which is especially good if I want to zoom in right on this S part here. If I just press zoom in, it's going to zoom into the center of whatever I'm looking at, which isn't what I want. I want to zoom in to where I just clicked, and that's right there. All right. So if I zoom into this val, again, I'm just going to take this stretch right here. What I can see is very clearly identifiable repeating patterns, right? So I can select this first one and notice that what I'm doing is I'm trying to select from the same landmark on the left edge as to the right edge, right? So I'm seeing the first dramatic change passing through that zero line, going in the upward direction. And it doesn't matter that that's what it is. It just matters that I do the same thing to start as I do to end. So the first zero crossing here, and then I'm ending it on the next major zero crossing of the same landmark. Right? So I have selected exactly one pitch period, okay? And I can see that it lasts 7.5 milliseconds. And I also see that I could fit 132 of these into 1 second. And now this becomes useful, right? Because now we can say, well, if the period is this, and that would be the frequency corresponding to the period, right? Those of you remember from exam 1, that means that the pitch, the fundamental frequency of this speech signal is 132 hertz, right? So just to remind you, if we zoom back at the whole thing, it's not how many of the whole syllable can fit into 1 second. That sort of doesn't matter, right, for right now. It's that each of these individual repeating patterns fits 132 into one second. So that'll let us know what the pitch, and in fact, if we say to Praat, show the pitch, right at that moment, I get 132 hertz, right? Because what it's doing is saying, what's the rate of repetition for things that look like they're the same moment to moment in time? And we can see that this blue mark, there are ways to be confused by this. So I want to spend a little bit of time to educate you a little bit on where to look, because we see a kind of red, and this might not show up very clearly on Zoom if you're looking at depending on your screen size, but I see this cross, this red cross here, and of course we see the time, 0.279. So that's exactly when I've clicked, and we see on the left 2,396 hertz. And there are two things you should keep in mind here. One is that that is not a reasonable fundamental frequency for any human voice. Even the smallest child could not have that as a fundamental frequency. And so what that's referring to is the spectrogram. The pitch is not directly represented on the spectrogram. It's just simply being drawn over top of it. So this blue line here doesn't correspond to the same frequency range we see on the left side from 0 to 5,000. The blue line has its own axis over on the right. And one of the ways that Praat can help you out in this is that when I click the red crosshairs on the spectrogram, that is in a red number. And if I click something on the blue, it'll show up in blue on the right. Okay, and the pitch range, as you can see, I've set this to go from 70 to 200. You might have a different range on your computer because you can just set the range to be whatever you want. And in fact, you can do that. If I go to pitch settings, I can show the range between any number and any other number. You might have it set by default to 500, in which case it'll look like this, right? So some of you might have been wondering, why does your pitch contour look so higher up on the screen than mine? It was because you were viewing from some low number to 500, in which case a lot of this range from 200 on upward was just sort of not being used, because this is my voice and I can't get anywhere near 500 hertz. So instead, because I know that the pitch range for this talker, who is me, actually, no, this was someone else. Anyway, for this talker, who's an adult male, I know that the pitch won't really go far below 70 or above 200. So if I set that range, that means that the whole range will be the range that's informative to me. So that's useful. So there are, as we've seen, two ways to get the pitch, right? I can go and zoom way in, and I can click on exactly how often one pitch period will last, or I could just click on it and just ask it to tell me the answer. Right? And even if it didn't tell me this, right? Even if we zoomed out a little bit, where I zoomed sort of accidentally correctly here, where all it's telling me is the duration. Now it's not telling me the periodicity rate, the repetition rate anymore, not because it doesn't exist, but because it just doesn't have room to show it on here. I could just take 1 and divide it by this number, and I would still get 132.3, right? So there's, you can compute it mathematically. You could have it calculated on top or on the side. In any case, it's all dealing with the same number, which is why we've, it should benefit you to remember the relationship between period and fundamental frequency. So we can zoom in, we can zoom out, we can show pitch or not. One thing you'll notice is that the pitch contour, this blue contour, is visible during the vowel, but it's not visible during this consonant. This is the S in sock, right? And the reason for that is that S doesn't have periodicity. If we zoomed into this, right, there's no part that's actually repeating moment to moment. Each of these, I mean, we can see individual peaks right here, but there's no consistent interval between those peaks. So without that consistent interval, we don't have periodicity. There's no regularity in that rate. It still has frequencies, but it doesn't have a fundamental frequency. The fundamental frequency is how often do we see whole chunks of the signal repeating. So this should be very visible in the vowel, because we see almost complete mirror images or copies of each repeating chunk. But for the k sound, we don't see that. It's just a lot of literally noise in this case, but nothing with any systematic pattern. Okay, so what we've been doing is just sort of poking around in the signal, making sure we know what it is we're looking at, making sure we know what the numbers are, what they correspond to here. What are the questions we have, having gone through what we just did here? What do we think?
Could you tell us one more time how you changed the Hertz values on the right-hand side?
Yeah, so on the right-hand side, what we have is our pitch range. And what I did was I went up to pitch up at the top, and the second option is pitch settings. And I clicked on that, and then the first two arguments here will set your upper and upper limit there.
Great, thank you.
And for now, I'm actually going to go up to pitch and just uncheck the show pitch button, just because it might just get in our way. Another thing I wanted to encourage you to do, so in case you're kind of formulating the question in your mind or maybe typing it out, if you want to go into the chat window and just sort of type something and say, I have a question, I'm about to type it, that'll make sure that I don't, talk over you or move on before you're ready to get that question out. Okay, so I'm looking at my list of things I wanted to show. Okay, so we have not only a range of pitch, which we can no longer see because we've deactivated the pitch, so those numbers went away. We can also do the same for the spectrogram. So we can either show it or not, but usually you want to see it. So I'm going to click on spectrogram settings. And just like for pitch, we can see, we can set the upper and lower boundaries. So in this case, I'm going to set it from 0 to 8,000, and I'll hit apply. And as we can see, we've sort of smushed the previous window of sound down farther so we can see a higher range of the frequency spectrum. And we can go even higher than that. I can go up to 12,000, right? And we're just systematically smushing down our representation here. What we can see is that for the S sound, we have strong frequency energy extending way up in the frequency range, right? So at the point where I've clicked right here, it's just about 10,000 hertz. And we're still seeing a decent amount of energy in the sound spectrogram there, which just goes to show, like, when you deal with a sound like S or other sibilant fricative sounds, you have really strong high frequency energy. The vowel, on the other hand, the strongest energy, if I click on the spectrogram, right, I've clicked right at the top edge of that dark bar, because the darkness of the bar shows us that at that frequency, that's where we have the strongest energy. And if I click right at the upper edge of that, it basically tops out at less than 1500 hertz. So a lot of vowels have energy primarily concentrated in the lower frequencies, whereas these fricative consonants are spread out to much higher range. So, and this is, this is the way that we find that out, right? So by clicking on this, we have an instantly, like an estimate of what those frequencies will be. Okay, so the thing is, though, if you just downloaded Praat recently, odds are when it showed up on your computer for the first time, it went up to 5,000 hertz. And this is a pretty decent range. It'll show you a lot of the information you'll need to understand speech acoustics and what frequencies are important. But suppose you wanted to look at specific kinds of information. Maybe I want to look at those lower vowel resonances, and I can set this to a lower frequency of, say, 3,000. Now I can see these in much more detail because the area of the screen that's devoted to that range is now occupying a larger area of my screen. You'll notice also, though, that we have these other numbers here. And odds are, if it's a new Praat download for you, you're seeing it look like this, right? Because the window length was set at 5 milliseconds. What this means is that every 5 milliseconds, it's taking a little snapshot of what frequencies are in the signal. And so what you get with that is a really good, accurate sampling in time. Because 5 milliseconds is pretty short, right? if you sampled anything 5 milliseconds at a time, you're going to get very good precision over time. And you can do the opposite. Suppose I wanted to take not 5 milliseconds, but 40 milliseconds. If I set that, now the spectrogram looks different. And it's not because the sound is different, it's because what we've prioritized in the analysis is different. Okay, so in this case, what I've said is, over a stretch of 40 milliseconds, what frequencies are there? And in this case, because of that longer analysis window, we can see in much more detail what frequencies. In fact, I can see individual harmonics in the spectrum. I can click on individual harmonics and see that each one is, as it would turn out, 132 hertz apart, because that's the fundamental. But what we lose by having this long of a window length is knowing exactly when these things happened. Because as you can see up on the waveform, even though we have those very clearly defined peaks in the waveform that correspond to the glottal pulses that we learned about last week, down here in the spectrogram, there is no such evidence of glottal pulsing. We see evidence of all the frequencies, but not those individual pulses. So if I go and make this 5 milliseconds again up at my window length, now, as it turns out, that's a fast enough sampling that I can see a pulse in the spectrogram for every single glottal pulse that we have in the waveform. So I've just shown you the difference between a broadband spectrogram, which is what we have here, and a narrowband spectrogram, which is what we have here. Now, the narrowness or broadness that we're talking about is the difference between narrow frequency range, which is what we have here. We have narrow differentiation between frequencies, or we have broad representation of frequencies like this. And again, the signal's unchanged. I haven't filtered the sound. All I've done is tell the computer, take a longer look at this signal. And the longer look you take, the better estimation you can produce for those frequencies. What do we think about that? That's I think mostly a new concept. We touched on it just a little bit in signals and systems, but what do we think about this here? We have a question about getting comfortable, playing around with the view range, window length, dynamic range. I would encourage you to play with this a little bit, and just basically within the range that I've shown you up on the screen here. I would say that a window length between 5 and 40, and I'm using millisecond terms, so 0.005 to 0.04 is basically those are the lower and upper ends that you probably find useful. If I make anything that's much outside that range, it's going to be rendered so extreme in one direction that it's going to be unuseful, like not useful, as you can see here. So like here, it's so smeared apart that the representation of frequency actually extends way beyond even where the val is. So it's good to play around with this just to see what is being represented, because you can see either really precise timing information or really precise frequency information. And I would also encourage you to, just as when you're viewing any graphical representation of data, know what the axes are, right? I'm viewing here from 0 to 0.68 seconds. I'm viewing on the left side from 0 to 3000 hertz. Therefore, if I see that these, let's put this somewhere in the middle here. If I see these vowel formants, we call these formants if they're dark bands on the spectrogram. If we see these that sort of extend right up into the middle of the spectrogram, we want to know what that middle means, right? It's the middle between 0 and 3000. So that's why it's right around 1500. So I would say it's a good thing to know how to change those things, because suppose you use your standards, right? The Praat, right, out of the box standards of 5 milliseconds, 0 to 5000 hertz, your dynamic range is 70. You can say, oh, it looks like most of the frequency information for the S is right here, and it's just a little bit of information. But if you went into this and set this range to view higher, let's say 8,000, you discovered that in fact, most of the energy was higher than 5,000. So that's just good to know, just to make sure you're viewing as much of the information as you need. The dynamic range feature, which we haven't talked about so far, what this refers to is relative to the loudest part of the signal, how far down into the quiet part are we going to look? So this is showing us the loudest 70 decibels in the signal. I usually set it a little bit lower than that, because as you can see right here during the silent part, there's a little bit of gray kind of schmutz on the screen, and that's not really important. In fact, it would be more distracting than helpful. So if I select this to be 55 instead, then from the uppermost intense part of the signal, I'm only going down up until 55 below that. And so for that part of the signal that I just showed you that is now gone, that was, as it turns out, at least 55 decibels softer than the loudest part of the signal. So by setting this at a lower level, what you do is remove some of the background noise and some of the lower parts of the signal, which you might not even want to be looking at. But careful that you don't set it too low, because if I just set this at, say, 20, right now, all I see is that resonance here, the third resonance of the vocal tract, and then we have a little bit of energy for the fricative, but now the signal looks basically empty, but we know that it's not. It's just that it has a pretty wide dynamic range of what's there. So I usually keep this around 55 for most recordings, and that's a pretty good starting point. Right, so looking for a couple more, if there are any more questions here in the chat box. I'm not seeing any. Okay, so what I want to do is call up a different sound that'll let me illustrate something else. I'm going to call up the sound hid. Okay, and I'm going to go back to my spectrogram settings and set it how I want. So I'm going to view only up until 5,000, and I'm going to set a 12 millisecond window length here. All right. And the reason I did this is because I'm interested in understanding this vowel. And vowels typically don't have a whole lot of energy above 5,000 hertz. But they do have energy in these bands in the lower frequency regions. And by lower, I mean just below 5,000. So if I click on this first one, right, what I'm doing visually is sort of tracking my cursor, my mouse along this part that's just a dark band. And that means that at whatever frequency corresponds to that height in the spectrogram, that's where I have a really strong resonant frequency. And we can see it's around 470 hertz. And then the second band up from that, right around here, about 2,140 hertz. The next one up from that, about 2,650. And then the next one up from that is about 3,260. So we have these frequencies of these bands, and it's not so important that you get this down to the single unit hertz, right? Depending on the exact pixel on my screen that I'm clicking on, this is going to change a little bit, which is why we're kind of ballparking it. But what we're viewing are the formant frequencies, the resonant vocal tract frequencies during this vowel. And so those would be pretty important to know as we're viewing that. Okay, so we can click on them and look off to the side here. I've clicked on exactly 3,200 hertz. So if there's something in the signal, I can just use as if you're just looking up on a graph how high something went. But another way of viewing these resonances is by going up to where it says Formant and clicking Show Formants. Okay, so now we have these red and pink dots that tell us where those resonant frequencies are. And there are some things to look out for, some little tricks that you want to be aware of. But for the most part, it is set up to analyze typical adult voices so that it'll have a good estimate of where these frequencies should be. For example, it knows that the first 3 frequencies that it estimates should be roughly below 3,000 hertz. And in fact, that's what we see. It's not going to try to find 3 resonant frequencies below 1,000 hertz because that's just not how a human vocal tract would work. So this is, mostly set up and optimized for speech. However, if you're analyzing the voice of a smaller talker, maybe it's a smaller person, maybe it's a child, then all of these resonant frequencies will be shifted upward and we know that that's just physically determined by how resonance works. People can also shift their formant frequencies up and down just by trying to imitate others' voices, right? I can imitate a really large person or a really small person. And in addition to changing the pitch of my voice, I've also kind of changed the length of my vocal tract. And so if you have someone with a voice that's anything other than what the default numbers would support, you can go and change that. You can go into the spectrogram settings, the formant settings. And just as you did for the other parameters, you can set where these are going to go. Now, this is getting a little bit too far deep into this for this particular class because this is just an introduction. But that's just to kind of plant the seed of caution, because if it gives you the wrong numbers, it doesn't mean that it's ground truth, right? It's just this is an option that's there, that it can be very useful, but it's only as useful as much as you know how to use it, right? So I'm going to turn that off for now. It's just oops. I'm going to turn that off for now just because we're not going to spend a whole lot more time talking about formants, but just to let you know that they're there. The final thing that we can, well, it's not the final, but another thing we can look at here is showing the pulses of periodicity. So I'm just going to zoom in so we can see these a little bit more clearly. So I'm going to highlight a selection and again, click the SEL button. It'll zoom right into where I clicked. And what it's trying to do here is separate successive pitch periods. And you'll notice it's not going to act the way a human observer would, in which case, like, we would clearly see this, peak here, and maybe that's our visual anchor for what it's doing. Now, it doesn't really care about those visual anchors. It's just performing an analysis where this is the chunk of the signal that's most like the chunk that came before it, and also, most like the chunk that came after it. So these blue lines won't necessarily line up exactly with where your eyes will go, but they're what's used by the computer to identify that periodicity. And we can see in this case that that periodicity is following through in between the I vowel and then the D, which we see here. So this part is that little moment in time in after the I where you're just producing like a sound, like hid, that. In fact, if you want, you can click on this part, click and drag it, and there are ways of playing just exactly the part of the signal that you've clicked or you've dragged here. So the way that I normally do it is just by pressing the tab key. And this is going to be a pretty hard signal to hear because it's just a very soft, low frequency signal. So going back out, I'm going to turn my pulses off. I'm going to just click and drag the vowel, and I'm going to hit the tab key on my keyboard. So notice I don't have to listen to the whole word. If I just want to listen to a very select part, I can do that. In fact, if I want to know why the first half of the vowel looks different on the spectrogram compared to the second half, I can do that. I can click on this part and then the second part, right? So there's a distinct difference in voice quality that changes from the first half of the vowel to the second half of the vowel. And I wouldn't have been able to pick that up if I'd listened to the whole thing. But by listening to individual stretches, I can do that. And I can do that with the closure here or just the D at the end. Okay, so this is one of the reasons why this program is really useful, is that if you want to get really into the details of the sound, you can do that. You'll notice though that if you click down here, in fact, let's go back to our first, this was a little bit better quality recording. If I go back into SOC and I have this single pitch period, okay, if I click on this, if I play it by pressing the tab key, it's really too short for me to pick up on what's going on. It just sounds like a little chirp because there are limitations on what our ears can derive from the sound as we're listening to this. So I might want to select, I don't know, like maybe 3 pitch periods. And now I can get that ah sound quality as you'd hear in the middle of the word sock. Okay. So one of the last things I want to show you about selecting sounds is a little trick that I was doing sort of in secret here that you weren't able to see. But notice if I'm selecting these regions, okay, now I'm just going to draw your attention to the fact that where I've selected here isn't any particular notable part of the sound wave, but it would be always in your best interest to play from an exact 0 crossing to another 0 crossing. And the reason is evident when you hear this sound. This sounds, in fact, I can make it a little bit more clear if we, well, I'll zoom out later, but the reason is that if you tell your speakers to immediately go out to this amount of displacement, they essentially aren't ramping up. They aren't smoothly getting there. They're trying to snap to that point. And when you have a snap, it's creating a click in the air. And so that click you hear might not actually be spoken, right? And that might not be part of the sound. That just might be an artifact of how you've told the speakers to behave by your computer. So what I would do is, so I go up to, well, I do this through the keyboard, but you can see what I'm doing here and saying, move the end of the selection to the nearest 0 crossing. Now keep your eye on this part of the signal right here where my cursor is and watch what happens. It's moved over just a little bit so that this part right here exactly is where the audio file is going to end if I play it. And the reason, there are lots of reasons to do this, one of which is that you don't want to be fooled into thinking that there's a click there. But also if you cut and paste parts of the sounds, you want to cut and paste it from this part because it's going to more easily transition into any other sound. And of course you can do this for the start of the selection as well. It's moved over. And what I tend to do is just with a keyboard, if you're on a PC, you can just hold the control key and hit the comma and period, which is basically just the left and right arrow, right? The less than, greater than sign. And it's just a quick little keyboard shortcut to make sure that as you're selecting things, you're selecting at a zero crossing. So there are lots of different tricks like this, both at the very broad level of figuring out where your selection starts and ends, figuring out exactly the rate of repetition. We've looked at resonant frequencies. We've looked at the range of how high the energy goes. We haven't looked so much at the intensity, but we can do that later. And then at the very, very nitty gritty level, right, where you're really getting into the sound details, you can still make very finely tuned selections that wouldn't be available in a basic sound player. So these are some of the reasons why I think it's useful to think about this. So I want to pause for a moment and open the floor for any questions that you might have about the things we were just looking at or anything related to that. You can pop a question in the chat window or just activate your microphone here. Okay, I'm not seeing anything pop up in the chat box, so that's fine. So as I mentioned before, you can play with the sound all you want, and it's not going to really jeopardize anything on your computer. But suppose I did want to make some new version of the sound. Here in the Praat objects window, there are a lot of different actions you can do. So you can find out things. You can query the sound by getting the intensity, the root mean square average of all the intensity values, the maximum, minimum, get the exact value at a particular time if you want that. You can do all sorts of things. You can analyze the pitch from this point. Just by using the defaults, you can get just the pitch contour itself, right? And there's lots of ways of extracting information out of that. You can do things like modify it. You can analyze the spectrum of it. So if I do that, I can call up that new object that it created called a spectrum, and now I have the spectrum. So we've had some experience looking at this in class before, and the way you'd work through this object here is the same way as you did with the spectrogram and the waveform. You can like click on individual things. Suppose I wanted to know, I can see this peak here. What frequency is that peak at? It's about 5,500 hertz, right? What frequency is this peak at? About 2080 hertz. So that's going to be useful information for us to pull out of the signal. I can also click and drag and press that SEL button just like I did before. And now all I'm looking at is the range between 0 and that upper limit that I clicked before. I can zoom in farther, right? And then continue zooming in just to see all the elements that I wanted. I can do that also within the sound itself. So I open up that sock sound again. Now, suppose I wanted a spectrum just of the vowel. I can just click and drag that vowel. And up in our spectrum dropdown at the bottom, it says view spectral slice. And now I have the spectrum of that exact part of the vowel. So for vowels, like I mentioned before, you're typically thinking about the lower frequencies. So I've zoomed down to the lower frequencies. And I can see here, in fact, that I have these lower frequency individual harmonics, and this should be reminiscent of what we looked at before, because if I click on the first one, it tells me that the frequency of where I clicked is 133, which is pretty close to the 132 that we measured as the fundamental frequency before. So the fundamental frequency we can measure by the reciprocal of what the duration was, the starting and the end point. We can just tell it to report the pitch for us on the right side of the graph. We can make a spectrum and just measure the lowest frequency harmonic that we saw. So there are lots of ways of getting information from this window here. So this is just a little bit of just a teaser of like all those different things you can do. And so as we move on and think about speech acoustics, we're going to be looking at lots of different things. We're going to look at how to understand the vowels that we see, how to pull out things like pitch, and manner of articulation. As we can see, if you call up the manner contrast various alveolars sound, there are all these different sounds that have a consonant followed by a. Right? So the idea is that all of these are alveolar or close to alveolar, right? We know that cha is not exactly alveolar, but it's close. And so the difference between these sounds, as you'll see, is how the intensity contour looks at the beginning of the syllable, right? And so later on in this sound, what I've done is try to chop away some of that vowel so that you can really zoom in to that consonant there, right? And as we can see, the shape of what the waveform looks like is the primary difference between these sounds, right? We can see also changes in the frequency content. We can see that there's this blob of darkness in the spectrogram right down here, and that blob is a little bit higher up for S than it is for ch, right? Then over here, for ya versus ra, we can see that where the frequencies transition during the sound is a big differentiator, right? For ya, we have this frequency that's sort of sweeping downward, whereas for ra, we have this frequency that's sweeping upward. So we can look at the physical differences between these sounds and begin to articulate, pun intended, between the physical changes that would occur and what they correspond to in the vocal tract, right? So even if we just looked at these first two, ch versus sa, right? We can see that for sa, we have this very gradual tapered onset of this noise, and then it gradually tapers down. But for cha, it rises to that full volume, in fact, a louder volume, even more quickly, right? And the reason for this is that it has roots in it being an affricate, right? An affricate sound involves buildup of air pressure, fully stopping that airflow as it goes through the vocal tract, and then releasing it very abruptly into this constriction. So what you see in this envelope here of the sound is a perfect reflection of that. We have a very rapid release, a rapid onset of this energy, and it also reaches a louder intensity, right? Because you've built it up and you're releasing it all at once rather than gradually building it on for the S sound, for the fricative. So we can see in these acoustic signals signatures of those specific vocal tract actions and begin to measure them on an objective level rather than just kind of describing them with our basic vocabulary. So I encourage you to continue, playing around with these sounds and just doing that, just playing around, seeing what this button does, seeing what that button does. You're not gonna ruin anything on the sounds because you can always download them again, even if you find a way of altering them and then saving them and accidentally changing them, it sort of doesn't matter because we're just playing around for now. And then as we continue learning about this program and learning about speech acoustics, it's going to be much more rewarding having learned how to do it yourself, because then you're not just limited to the handful of examples that I'll show you in class, but in fact can just go out and analyze anything you care for on your own. So we're just about out of time for today's class. I'm going to stick around for a few more minutes in case people have any questions. But if not, I will be seeing you all on Thursday and hope you have a good one.
Thank you.